Let's use MATLAB to solve a differential equation. Then we're going to do just a simple projectile in a constant gravitational field. All right, so let's start MATLAB. And let's create a script, a new script. And I'm going to define first a function which is going to specify what the differential equation is, the time rate of change of the state of the projectile. So I'm going to call the projectile state S, and so the time derivative of S will be S dot. So that's the name I use for S dot, and that is going to be defined as a function F, and F is going to be a function of the state S. Alright, so inside the state I need to define some things. One is the mass of the projectile. Mass, M, is equal to 10, I'll pick 10 kilograms. So that's the mass of the projectile in kilograms. I need to define the force of gravity, G, which is 9.81 approximately force of gravity per unit mass, and that has units of newtons per kilogram or units of acceleration in meters per second squared. And then I can extract the instantaneous state of the system, and that will be the position or the height of the object, which I'll call Z. So Z is going to be the vertical coordinate pointing upwards, so that's S1, and then the velocity, V, is going to be S2. So the state of the particle, of the projectile, is a two-parameter state, the position and the velocity, and so we define it as a vector S, and then we extract the first element to get the position of the vector S and the second element to get its velocity. All right, if we know S and V, we can now define the time rate of change of Z and V. So Z dot, which is the time derivative of the position, well, that's just by definition the velocity, so that's just going to be V. And then V dot, which is the acceleration, will be minus G over M, right? Because M times the mass times acceleration is equal to the force. All right, so, V dot is just, no, not V over M, just minus G, yeah. Right, that's the acceleration, and the acceleration is minus G. Okay, so this is time derivative of position, and this is the time derivative of the velocity or the acceleration. And it's also the velocity. Yeah, the typo. All right, so once I've created the time rate of change of the position, I can pack them back into a vector S dot, which is the time derivative of the state. So that will be Z dot, V dot. So this is the time derivative of the state. And then I type end. All right, so that defines F equals ma. Okay, so now we projectile motion. We should define initial conditions. So Z0 is equal to 0. This will be the initial position in meters. V0 is 10, is the initial velocity in meters per second. And then S is equal to, S is equal to Z0 semicolon V0, so that's the initial position. And now we're going to simulate the trajectory of the particle using some method called Euler's method. So we know the time rate of change is F of S, and then if we want to get the change in the position, we just multiply the time rate of change by a small increment of time. So that small increment of time, I'm going to call it dt, and it's going to be 0.01 seconds, so in seconds. So that's the delta t is a small change in time. And then we're going to define the initial time, t is equal to 0. Oops, over here. And now we are ready to simulate, and we're going to do it using a construct called a while loop. So while t is less than, let's say, 25. So we're going to simulate for 25 seconds. And we're going to, inside the loop, we're going to increment t by t plus delta t. So each time we go through the loop, the old value of t will be replaced by a new value of t, which is the old value plus delta t plus dt. And so t is getting bigger, it starts at 0, and we'll increment by 0.01 at each time we go through the loop. And we're going to keep going, looping around until t reaches or passes 25. And then we can define the new state. So the new state, s, will be equal to the old state, s, plus dt times f of s, the time rate of change of the state, right? That's just s dot. And then we can now plot the position, the instantaneous position of the projectile. So at times t, we're going to plot the position, which will be s of 1, right? The first element of s is the position. And we're going to plot it using a little symbol, which is going to be a little circle. All right. And then hold on. So the hold on, each time we plot, we would erase the previous plot. If we do hold on, it'll just keep the old plot on top of one another. So it'll keep plotting the symbols, and we're able to see the trajectory of the particle, or the projectile, as a function of time. And then we can end the while loop. And then we can draw it. So at the end, we'll put the grid on and draw now. All right, let's go through this one more time to make sure it's good before we go. I'm going to add some space in here, since all these are inside the same loop. All right, so this here defines the time derivative of the state, and the mass of the object is 10, g is the acceleration, 9.81, z is the z is the height, which is given by s1, v is the velocity given by s2, z dot, the time derivative of the position, is just the velocity, and the time derivative v dot of the velocity is the acceleration, which is minus g. Remember, we put minus g because gravity points downwards. And then we pack back together the time derivative of the state, which is a two-component vector, first z dot, then v dot. All right, then we come back to the top and we set up the initial state, z naught, v naught, the initial time, the time increment, and now we're going to loop, starting with t0, t equals t plus dt, and s is the old state, s plus dt times ds dt. Right, remember f of s, this is the same thing as s at times t plus dt is equal to s at times t plus dt times ds dt. Right, so you can think of it as just s plus ds. This is called Euler forward method to integrate a differential equation. All right, let's run it, see if it works. Fingers crossed. Oh, I forgot to save it. My projectile.m. Save. And is it running? Oh, yeah, there it is. So here it goes up, and we can't really see it, but we can zoom in. Let's zoom in a little bit, make sure it did go up. How do I make it bigger? So it starts off and it goes up and then back down. So maybe I can run it for a little bit less time. For 25 is too long. So let me kill it. Let's run it for 4 seconds instead. Right, you toss the ball up at 10 meters per second. It's not going to take very long before it hits back the ground. So let's try it. Run for only 4 seconds. Let's run it again. Oh, I have to erase the old plot, did I? Hold on. Clear all, close all, my projectile. Did I save it? Let's try it this way. Alright, there we go. See the trajectory. So this is the time axis along here, and this is the z-axis. So let's do it one more time. I'm going to change one more thing. I'll run it for even shorter, just 2 seconds. T less than 2. And then grid on, and I'm going to do X label. The X label is the time axis, time in seconds. The Y label is going to be the height in meters. And I guess that's it. Let's run it again. Oh, let's put a grid on it too. Oh yeah, I do have a grid. Okay. Alright, there's the picture again. For only, oh, I didn't save it. I want to do it for only 4 seconds. For 2 seconds. What else do I want to do? Oh yeah, change the font size. Because it's hard to read. Set, get current axis, font size 16. So 16 is a bigger font. Run it. Alright, there's the picture. So let's make it bigger so you can see. So at each point along the while loop, it plotted a little symbol. And this sort of describes the trajectory of the particle. Now it's an approximate one because we have a finite time step size. So let's plot the exact solution we would get from calculus on top of it to see how well the Euler-Ford numerical method did. Alright, so let's plot on top of this the analytic solution. So plot, let's define the t. T is equal to 0 by dt plus up to 2 seconds. And then the solution, I'll call it capital Z, is going to be minus g times t dot hat 2. So the dot hat means I want to square each and every element of t. Right, so remember the solution is z equals minus gt squared, a half, 0.5 plus v0 star t plus z0, right? This is the solution. Analytic solution to the projectile motion. And now we're going to plot that plot t and z, and we're going to plot it using a red line. And over here, I'm going to plot all these using blue circles. So the little b means a blue, and the little r means red. All right, let's clear the figure. Did I do that already? Okay, so clear all, close all, save and run. Oops, I got a mistake. Oh, I don't know what g is out here, so I have to redefine g is equal to 9.81. And clear all, close all, run it again. All right, so you can see, well, I don't know if you can see. Let me make it bigger. Right, you see a little bit of an error. Oops. Right, the red line is the exact solution, and the blue curve is the one we get using Euler-Ford, and you can see a little discrepancy up here, right? If I zoom in, you can see that they are not quite the same. There's an error, and that's because I have a finite step size. So if we want to get a more accurate solution, what we can do is make dt smaller. So let me try again, changing my value of dt. So coming up here, I'm going to change dt, I'm going to divide it by 10, so it'll be 10 times smaller. Close all, clear all, and then run it again. And now the error is much smaller, so let's zoom in. Right, you can't see the difference really now. Even when I zoom in, there's still going to be an error, right? You can still see it, but you have to zoom in quite a bit because I made delta t smaller. And you can keep going that way. So this is an example of solving a differential equation using Euler's method. All right, that's it for today. Bye.